Okay, so this is our next section on Pythagorean Theorem. So our learning goals are I can use the Pythagorean Theorem to solve for missing measures in right triangles, and I can use the converse of the Pythagorean Theorem to determine whether a triangle is acute, right, or obtuse. So let's recall a triangle is a right, if a triangle is a right triangle, then the square of the length of the hypotenuse is equal to the sum of the square of the length of the legs. So we have hypotenuse squared is equal to leg 1 squared plus leg 2 squared, or our equation that we know, c squared equals a squared plus b squared. A Pythagorean triple is a set of positive whole numbers a, b, and c that satisfy or make true the equation c squared equals a squared plus b squared. So common Pythagorean triples are 3, 4, 5, 6, 8, 10, 5, 12, 13, 7, 24, 25. So they're all positive, and when you plug them into our equation, it makes it true. So using the Pythagorean theorem to answer, using Pythagorean theorem, and then we're going to write our answers in simplest radical form. So that means we're going to have no decimal, there's going to be the square root, and then we're going to determine if the three lengths form a Pythagorean triple. So are they going to be whole numbers? So A, across from our right angle, that's always our C. So we have x squared equals 12 squared plus 9 squared. So x squared equals 144 plus 81. Add those two bad boys together, we get 225. Take the square root of both sides. We get x equals, and if we look, 225 is a perfect square, so it's on our list. So it's x equals 15. So our numbers are 9, 12, and 15, which is a Pythagorean triple. They're all whole numbers. Okay, B, across from our right angle is our C. So we have 10 squared equals x squared plus 4 squared. So 100 equals x squared plus 16. Subtract 16 from both sides. We get, I'm going to flip it around, x squared equals 84. Take the square root of both sides. We get x equals, okay, 84, it's not a perfect square, but we do know we can break that down into 4, square root of 4 times the square root of 21. So x is 2 square roots of 21. So do the sides, 4, 10, and square root of 21. Does it create a Pythagorean triple? No, it does not. Okay. So our 9 is our c squared. So we have 9 squared equals x squared plus 6 squared. 9 squared is 81, so we have 81 equal to x squared plus 36. Subtract 36 from both sides. We get 45 equals x squared. Okay, I'm going to flip it around. So we're going to take the square root. We get x equal to, okay, 45 is not a perfect square, but we do know it can be rewritten as square root of 9 times the square root of 5. Square root of 9 is 3, so we have 3 square roots of 5. So is this a Pythagorean triple? Does 9, 6, and 3 square roots of 5 create a Pythagorean triple? No, it does not, because it's not whole numbers. Okay, flip the page. So Determine whether 3 given lengths form a Pythagorean triple. So how do we know if each set of these form a Pythagorean triple? Well, we know that they're all positive whole numbers, yes, but does it satisfy our Pythagorean theorem? So if we plug it in, our biggest number is always our C. Okay, so your biggest number is your C. So 7 squared, let's see how that compares to 4 squared plus 5 squared. 7 squared is 49. 4 squared is 16. Plus 5 squared is 25. 16 plus 25 is 41. So 49 is not equal to 41. So this does not satisfy, does not form a Pythagorean triple. Okay? B, again, remember our biggest number is our C. So 17 is our C. So 17 squared, I'm just going to put a little box because we don't know if it's equal yet or not, is equal to 8 squared plus 15 squared. 17 squared is 289, and we're going to see how that compares to 64 plus 225. So 289, see how that compares? So 64 plus 225 is 289. So 289 is equal to 289. So yes, 8, 15, and 17 are a Pythagorean triple. Okay, so we have an application of the Pythagorean theorem. So you just picked up a ground ball on first base. So we're right here on first base. You see the other team's player running towards third base. So they're running towards third base. You have to throw the ball from first to third to get the runner out. So here's our little triangle. Okay. We're trying to throw from first to third. How far do you have to throw the ball from first to third base to get the runner out? So we're trying to find this length right here. We know that this is a right angle on this baseball diamond. So our X is actually our C. That's across from our right angle. So we can use Pythagorean theorem to find that length. So X squared is equal to 90 squared plus 90 squared. So X squared is equal to, if we plug these in, so I'll show you what I'm doing. So on your calculator, if you just do this, 90 squared plus 90 squared, to save us a little bit of time, add that together, we get 16,200. Take the square root of both sides. So on application problems, it's okay to, you don't have to figure out our simplest form. We'll just take the square root. So square root symbol of 16,200. That gets us 127.3 feet, because we know that our unit is feet. I know this calculator kind of shows you the simplest form, but we want that decimal in this application problem. If you don't remember how to take square root on our calculator, you have to hit the second button. I think it's second and then x squared, and because above it is that little radical. And then you should see it come up like this on your screen. Okay, find the value of x. So to find x, we actually have to find this segment in between. So I like to call this segment that's in between y. So we need to find y first. Because to use Pythagorean theorem, you need to have two values. So to find y first, we have to do Pythagorean theorem twice. So 25 squared is equal to y squared plus 10 squared. 25 squared is 625, and that's equal to y squared plus 100. Subtract 100 from both sides. We get 525 is y squared. So a little trick before we keep solving. In this other equation, to find x, we know that 28 squared is equal to x squared plus y squared. Well, we know y squared. So 28 squared is equal to x squared plus 525. 28 squared is 784. That's equal to x squared. Subtract 525 from both sides. X squared is 259. Take the square root of both sides now. And you get x is equal to 16.1. Okay, again, another picture. Find the value of x. Of course, my picture is broken. It's not here. Okay. So to find x, we actually need to find, again, two separate little lengths. So let's call this one y and this one w. We know that x is equal to y plus w, so we need to find those two lengths. So let's first find y. So in this triangle, we know that 14 squared is equal to y squared plus 12 squared. So 196 is equal to y squared plus 144. Subtract 144. We get 52 is equal to y squared. Take the square root of both sides. Y is 7.2. So we found y. So we're one step closer to finding x. We're just going to find w. So in w's triangle, we know that 29 squared is equal to w squared plus 12 squared. 29 squared is 841. That's equal to w squared plus 144. Subtract 144 from both sides. We get 697 is equal to w squared. Take the square root. W is 26.4. So now we found w. So x is 7.2 plus 26.4. So x is 33.6. Okay, a triangle has side lengths 12.5, 30, and 32.5. Is it a right triangle? So how do we know if it's a right triangle? Well, one way to check is to see if it satisfies the Pythagorean theorem. So our base value, remember that's always your C, 32.5. We'll see how that compares to 30 squared plus 12.5 squared. So 32.5 squared is 1056.25. And compare that. 30 squared is 900 plus 12.5 squared is 156.25. If you add that together, we get 1056.25, which is equal to 1056.25. So yes, these side lengths create a right triangle because it satisfies the Pythagorean theorem. So that leads us to converse of the Pythagorean theorem. So converse of the Pythagorean theorem is when you're given a side of a triangle A, B, and C, if c squared is equal to a squared plus b squared, then the triangle is a right triangle. If c squared is greater than a squared plus b squared, then the triangle is obtuse. If c squared is less than a squared plus b squared, then the triangle is acute. Because of this converse, it's always best to keep c squared on the left side to avoid confusion when you're classifying. So let's do a couple examples of classifying sides of a triangle. So if we have 3, 5, and 7. So 3, 5, and 7, one thing that's good is check to see if it can make the triangle. So 3 plus 5 is greater than 7. So it makes a triangle. If it was less than 7 or equal to 7, it doesn't make a triangle. Now we can do 7 squared and compare it to 5 squared plus 3 squared, because this is our C. So 49, comparing it to 25 plus 9. 25 plus 9 ends up being 34. So 49 is greater than 34, so this is obtuse. Okay. Next one. So the square root of 124, this is 11.1. So this is our C because it's actually bigger. So we know that 8 plus 9 is greater than square root of 124. So it can make a triangle with those sides. Makes a triangle. Now we can double check and see what type of triangle. So the square root of 124 squared, see how that compares to 89, or 8 squared plus 9 squared, not 89. So square root of 124 squared, the square root and the squared, they cancel each other out. So that's just 124. And we're going to see that compares to 64 plus 81. Bring down your 124. 64 plus 81 is 145, which is greater than 124. So this is an acute triangle. Okay, last one. Let's just double check and make sure this makes a triangle. So 0.5 plus 1.2, that's greater than 1.3. So this makes a triangle. So 1.3 squared, see how that compares to 1.2 squared plus 0.5 squared. 1.3 squared is 1.69. 1.2 squared is 1.44 plus 0.5 squared is 0.25. If you add those together, that becomes 1.69, which is equal to 1.69. So this is a right triangle. Okay, and that is the end of Pythagorean theorem and converse of a Pythagorean theorem notes. So your homework is going to be passed. Oh no, your homework is Unit 3, Lesson 3 in your worksheet packet.